Good afternoon, class. Today we are going to conclude Chapter 6. Let's start by talking about double and triple bonds. A double bond happens when atoms share two pairs of electrons instead of just one. This only happens when there are not enough electrons to complete octets given the 2 or 3 elements that you have to work with. Sometimes a triple bond also occurs, and this happens when atoms share 3 pairs of electrons. Again, for the same reason, this happens when there are not enough electrons to complete octets. Not enough electrons. While the octet rule is useful, there are some exceptions. We've already talked about hydrogen. Hydrogen requires just 2 electrons to form a noble gas arrangement. Other nonmetals, such as phosphorus, sulfur, chlorine, and bromine, and iodine can form compounds with 10 or 12 valence electrons. So they can have 8, 10, or 12. The sulfur atom has an octet in many compounds, but for example, in SF6 there are 12 valence electrons, or 6 bonds. Remember that each bond represents a sharing of 2 electrons. 2, 4, 6, 8, 10, 12. So the sulfur in this case has 12 valence electrons. Let's look at another exemption. Boron likes to form only 6. So you can see here in BCl3 that boron likes to form a molecule and have only 6 valence electrons instead of 8. Again, boron likes to form 6 instead of 8. So the exceptions that you should know are that hydrogen and boron like less than 8, and phosphorus, sulfur, chlorine, bromine, and iodine can form compounds with more than 8. The electronegativity of an atom is its ability to attract the shared electrons in a bond. It increases from left to right going across the periodic table. It also increases from the bottom to the top. So if you remember in the previous lecture, we mentioned it increases as you go up and towards the right. Electronegativity is high for nonmetals, with fluorine having the highest electronegativity, and is low for metals. Noble gases do not have electronegativity values because electronegativity is a measure of an atom's ability to attract shared electrons in a bond. Most noble gases already have 8 valence electrons and don't generally like to bond, so we don't give them electronegativity values. Here is a piece of the periodic table showing some of the values. You will notice that fluorine has a 4.0, which is the highest. The smallest on this table is cesium at 0.7. So again, it is high for nonmetals, low for metals, and increases as you go up the periodic table, and increases left to right for an overall trend of up and to the right. The difference in the electronegativity of bonding atoms can be used to predict something we call the polarity of the bond. In the H2 molecule, electrons are shared equally and the bond is considered nonpolar. In the HCl molecules, electrons are shared very unequally, and we call this bond polar. So let's talk a little bit more about what polarity is. A perfectly equal sharing of electrons, such as what happens between 2 elements with the exact same electronegativity, is what we call a nonpolar covalent bond. It is an equal or almost perfectly equal sharing of the electrons between the 2 atoms. These typically have a very small electronegativity difference between them. In the case of hydrogen bonded to hydrogen, the difference in electronegativities is 0, since they both have the same electronegativity value. A polar covalent bond happens between nonmetal atoms, and it is an unequal sharing of electrons, has a moderate electronegativity difference. In a polar covalent bond, which is typically between a metal and a nonmetal, the difference in electronegativity is larger. We have a separation of charges that we call a dipole, meaning 2 poles. You can think of it like a magnet with a north pole and a south pole, only in this case we have a positive charge and a negative charge. We use the lowercase Greek letter delta with the positive or the negative to show the charges, and an arrow with a slash on the end to show which way, from positive pointing towards negative. So again, the arrow points from the positive end of the molecule towards the negative. An ionic bond is what happens between metal and nonmetal ions. This is the result of electron transfer, meaning there is no sharing at all. So in a nonpolar covalent bond, we have almost equal sharing. Polar covalent, we have an unequal sharing. And ionic bonds, we have no sharing at all. The electron is completely transferred from the metal to the nonmetal. We can tell whether something will be we can tell whether something will be nonpolar covalent, polar, or ionic based on the electronegativity differences. If the difference is very small, between 0 and 0.4, the bond is nonpolar covalent. If the difference is moderate, between 0.5 and 1.8, the bond is polar covalent. If the difference is larger than 1.8, it is considered a very large difference, and the bond is ionic. In this case, the electrons are considered transferred and are no longer shared. We have a theory called the valence shell electron pair repulsion theory. This theory describes what the shape of a molecule looks like. It describes how the electron groups are oriented around the central atom. It states that these groups are arranged as far apart as possible around the central atom. And it states that the specific shape of a molecule is determined by both the number of atoms attached to the central atom and the electrons that are not involved in bonding. For example, in a molecule of carbon dioxide, there are 2 electron groups around the central atom, carbon. 2 oxygens. These want to be as far apart from each other as possible. The furthest apart they could possibly get is a linear arrangement with a bond angle of 180 degrees. The shape of these 2 groups around the central atom is linear. Linear, again, that is because they couldn't possibly get any further apart from each other. If, however, you have 3 electron groups around the central atom, such as in ch2o, the repulsion is minimized by placing the 3 groups as far apart as possible. If you take a circle and divide it into 3 pieces, 360 degrees divided by 3 gives you bond angles of 120 degrees. Again, these are as far apart as they can possibly be. We call this shape trigonal planar. The trigonal because it is shaped like a triangle, and planar because it is flat. Trigonal planar, shaped like a triangle and flat. Let's look at something like, instead, sulfur dioxide, SO2. There are 3 electron groups around the central atom. There are 2 oxygens and a pair of electrons that are not participating in the bonding. The repulsion is minimized by placing the whole thing in a trigonal planar shape. The 2 molecules at either end and the lone pair of electrons on the top corner. So again, this is trigonal planar. However, the shape of the molecule, not taking into account those lone pair of electrons, is bent with an angle of 120 degrees. If you imagine those lone pair of electrons as being up here, you also have 120 degrees between this atom and the lone pairs, and 120 degrees between this atom and the lone pairs. In a molecule like ammonia, NH3, you have 4 electron groups, 3 of which are hydrogen atoms and 1 lone pair around the central atom of nitrogen. We minimize the repulsion by placing the 4 electron groups at the corners of a tetrahedron, with bond angles of a little bit less than 120, or around 109. The shape of the 3 bonds and the lone pair on the central atom is called trigonal pyramidal. Trigonal pyramidal. And again, it looks like this. With the electrons, the shape is a tetrahedron. If you ignore the electrons and only look at the shape of the molecule, it looks like a triangular pyramid, or trigonal pyramidal. In a molecule like water, where you have also 4 electron groups, 2 of which are the hydrogens bonded to the oxygen, and 2 of which are the lone pairs. If you take into account the shape of the whole thing, you have a tetrahedral shape, right? Just like you have in the molecule above. If you only look at the shape of the molecule without its lone pairs, it is a bent shape. Now let's talk a little bit more about polarity. So molecules can be polar just like bonds can be polar. Nonpolar molecules such as H2, Cl2, and O2 are nonpolar because they contain only nonpolar bonds. And again, if we go back and we look at our values here, remember that nonpolar is between 0 and 0.4. So if none of the bonds in your molecule are polar, then your overall molecule is nonpolar. If you have a molecule that has bonds that are polar, the molecule itself can still be nonpolar if the bonds, the polar bonds, cancel in a symmetrical arrangement. This happens in a molecule like carbon dioxide, where the direction of polarity is from the central carbon out towards the oxygens. If you can imagine those oxygens as playing tug of war with the carbon in the middle, since the oxygens both have equal pull but in opposite directions, they cancel each other out. Another example of this is CCl4, or carbon tetrachloride. You will notice that the chlorines are much more electronegative than the carbon. However, everybody's pulling on the carbon with the same strength and the dipoles cancel each other out. Therefore, the molecule is overall nonpolar, even though it has polar bonds. Molecules that are polar, such as HCl, are polar because one end of the molecule is more negatively charged than the other. The polar bonds in the molecule do not cancel each other out, and the electrons are shared unequally in the polar covalent bond. So in this example, the chlorine is pulling on the electrons much harder, and so the electrons are spending more time around the chlorine than they are around the hydrogen, meaning that the end of this molecule is more negative on the chlorine end and more positive on the hydrogen end. Another example of a polar molecule is water. There are two lone pairs and two bonds around the central atom. The oxygen is much more electronegative than the two hydrogens on the other end. So therefore, the direction of electron flow is in towards the oxygen. Since the dipoles are not equal and opposite because the molecule is bent, not linear, the molecule is more positive at one end and more negative at the other. In this case, it is more negative around the oxygen and more positive on the hydrogen ends. Another great example of this is NH3. There is a lone pair on the nitrogen and 3 bonds around the central atom. Those 3 bonds are not in equal and opposite directions. You can see from this drawing here that the 2 hydrogens are much closer to each other than this third. So we have a pull from one end, more negative end here, and a more positive end here. One way to tell whether a molecule is polar or nonpolar is to look at whether or not there are lone pairs. If there are lone pairs on the molecule is most likely polar. This is not a hard and fast rule, but if you're unsure and a molecule has lone pairs, 9 times out of 10 it's polar. Let's talk about some other attractive forces in compounds. There are several: dipole-dipole, hydrogen bonds, dispersion forces. In covalent compounds, polar molecules have attractive forces called dipole-dipole attractions. They also form strong dipole attractions called hydrogen bonds. Hydrogen bonds occur only if a hydrogen atom is bonded to a fluorine, oxygen, or nitrogen, and is then attracted to the lone pair on another fluorine, oxygen, or nitrogen. So again, in order to have hydrogen bonding, you must have a hydrogen, of course, and a fluorine, oxygen, or a nitrogen. Hydrogen bonds are the strongest of all of the forces that we're going to talk about today, and they exist between molecules. They play a major role in the shape of your DNA. So again, between a hydrogen bonded to a nitrogen, oxygen, or fluorine, and that hydrogen is then attracted to the lone pair on the next molecule. Dipole-dipole attractions are the next strongest of the attractions. They are nowhere near as strong as hydrogen bonds. And then finally, we have dispersion forces, which are the weakest of the three types. These are weak attractions between completely nonpolar molecules that are caused by temporary dipoles that develop when molecules bump into each other. They are weak, but they make it possible for nonpolar molecules to form liquids and solids. Without these forces, nonpolar molecules would only form gases. The melting point of a compound is directly related to the strength of the attractive forces between molecules and compounds. The stronger the attractive forces, the higher the melting point. So for example, a compound with weak forces such as dispersion forces would have a lower melting point. If you have hydrogen bonding, your melting point would be much higher. Melting points are highest in ionic compounds due to the extremely strong attractive forces between the ions in a compound. Remember that in an ionic compound, you have a positively charged ion and a negatively charged ion. These bond very strongly due to their opposite charges. This concludes Chapter 6, Part 3. Thank you for listening.